want to study population growth. So again, you need to apply how populations are distributed, and you also need to be able to explain how populations change over time and also how they're sustained. So what could lead to an increase in a population? You could probably think of a number of different things on your own. Hopefully you've done that. You could think about things moving into the population. You could think about birth, all sorts of things. The ones I really want you to focus on are these. First of all, immigration. To immigrate means to actually move into. So these individuals move into a population. Birth, the increase in the number of individuals in a population. Obviously, when an organism is giving birth, that increases the number of organisms. What could lead to a decrease in the population are the opposite of these things. So instead of immigration, we see emigration, and this is the movement of individuals out of a population. Instead of birth, we see death. So obviously death decreases the population. So population growth rate is a key word I want you to know. In fact, we'll do a couple practice problems with this in class tomorrow. You basically take your birth rate, subtract your death rate, and you multiply this by the number of individuals. This will tell you how much your population is actually growing. If you look at this school population, a fish, what we would take is the birth rate minus the death rate, and as we said above here, multiply it by the current number of individuals. For biotic potential, another key term I want you to know, this is the maximum rate of increase per organism under ideal conditions. So this is how fast you'll see actual growth when you have ideal conditions within the population. This rate depends on the age of each generation in which it starts to reproduce. So if you think about dogs versus humans, okay, in a matter of 2 or 3 years, typically 2 years, dogs can start to reproduce. Humans, on the other hand, think about how long it takes for an individual to reach sexual maturity. That might be 13, 14, maybe even years past that. You also want to look at how often an individual reproduces. Okay, so for humans example, we take a while to reproduce, but also the gestational period is 9 months versus a fish, we're looking at, maybe a number of days here. If you look at elephants actually carry their young almost 2 years. I believe it's about 18 months or so. You can also look at how many offspring are produced. So a lot of organisms will produce a number of offspring. Think about like sea turtles. They lay their eggs, they leave their eggs, they produce a lot of young, but not all the young actually survive. Again, if you think of most mammals, they're going to maybe have 1 or 2 organisms on maybe an annual or biannual rate. The human population, our biotic potential is growing about 6% each year. So we are continuing to grow, and we've sort of sidestepped some boundaries. Obviously, we're able to live in places we may have never been able to live because we're able to transfer water and food and other resources that we need and protection. Rats' biotic potential is 1.5% each day. Remember, we said rats are a generalist species, so they can live just about in any type of condition. They can rely on any source of food, and they rapidly multiply. Bunnies are or rabbits are very similar to this. Bacteria biotic potential is much faster. If you give bacteria the ideal conditions they need, you give them food, you give them the right temperature, you give them space for growth, they can multiply about 250% an hour. Okay, so think about one bacteria and how quickly that would multiply. There are a couple models of population growth you need to understand. In all of these population growth models depend and are determined by the amount of resources available. You've probably heard of these growth terms before: exponential growth and logistic growth. So let's look at our first one. In exponential growth, we see rapid growth that occurs when a population grows under ideal conditions. That means resources are unlimited. So think about maybe rats or think about bacteria. Okay, if they invade a body, they have ideal conditions, you will see that they rapidly increase. So if you increase the amount of time, you're going to see that population rise as you see in this image to the right. There is a lagging phase, so this is the slow growth period, and you can see that happens initially, okay, and then it exponentially increases past that. You'll also see that an exponential growth has a J-shaped curve. You see that lag phase, and then you see it shoot up. You'll also notice that there is increased birth and immigration when we see exponential growth. So we see rapid multiplication or reproduction, and you can also see a growth in immigration. Here's an example of bacteria, for example. If we look at this here, okay, you can see that first image in the top left. You only see a couple different cultures of bacteria in there that's growing on the agar. Agar is a mixture of beef broth and actually gelatin, and it gives it almost like this jello-like substance, and it gives it the nutrients that the bacteria needs. In the second picture to the right on the top, you can see those cultures grow. So they have the right temperature, maybe they're in an incubator, they have all the food resources that they need, and then you can see at the bottom left here, that bottom left one, you can see that they continue to grow in the middle, and then towards the end here, you can see that rapid growth towards the end. Now, obviously, a population can't sustain exponential growth. Think about why. That population will eventually run out of space. As you see in this last petri dish off to the right on the bottom, they'll eventually run out of space. They'll eventually run out of food stores. They're going to get backed up into their own waste. So you will eventually see that exponential growth. You will see a decrease. It cannot maintain, a population cannot maintain exponential growth forever. And this kind of goes directly with that. Eventually population reaches what we know as carrying capacity. And this is the maximum number of individuals of a population that an environment can sustain for a long period of time. I'll show you an image of what this looks like. So you'll see that when we have an increase in population, we obviously have a decrease in resources because organisms depend on the resources. They're feeding off those resources. That maybe it's space is a resource. Therefore, there's less individuals that are going to be born, and more may die from deficiency because they're not getting the resources they need. That's why organisms eventually reach this carrying capacity. So let's take a look at the logistic growth model. And if you already look over at the image on the right, you can see it starts off looking like an exponential growth. You can see the lagging phase, it rises, and then if you look at that dotted line, that's the carrying capacity here. So this is growth that may be followed by the exponential growth, and this is when a population's growth slows down or levels off. Okay, leveling, we mean it's kind of going even, where you can see on that dotted line. It meets carrying capacity. The shape of this curve is an S-shaped curve, and obviously you can see that. It also occurs when immigration or emigration, when organisms are leaving an environment, and also when death exceed immigration and birth. Environmental resistance. Make sure you know this term as well. This is a combined effects of all the factors that limit population growth. This resistance is a force that opposes biotic potential. Okay, so make sure you go back on that. All those effects that limit population growth. Like I said, environmental resistance could be space. It could be competition for resources. It could be predator-prey relationships. Those are all examples of environmental resistance. Lastly here, I want you to think of these factors that limit population growth. A limiting factor is a factor that has the greatest effect in keeping a population size down. Here are some examples. You have some density-dependent factors. This means that these are factors that are affected by how many individuals live in an area. Okay, so if you have a lot of organisms living in the same environment, same area, You could see increased competition. You could see increased predation, increased parasitism where parasites are passed, increased disease, okay? Think about a city. We have lots of people in that area. Disease can spread pretty rapidly. So density dependent means they depend on the density of your population. Lastly, we have density independent factors. These are environmental aspects that are not affected by how many individuals live in an area. These are typically abiotic. They're non-living. So this could be weather, natural disasters. Think of like tsunamis or hurricanes or tornadoes. These are density independent factors. It doesn't matter on how big your population is. These are just factors that could decrease the size or the growth of a population. And also human activity. Think about what we do as humans. We deforest forests, so we have a lot of deforestation going on to increase agriculture for supply and demand of resources. We also increase, we play a direct effect in global warming, all sorts of things in which we actually affect the size of populations. Make sure you go back and review this tonight, and we're going to definitely practice this tomorrow when you come to class.